Alright team, welcome back to The Explainer. Today, we're diving headfirst into an absolute masterclass on advanced web reconnaissance, designed specifically for you, security researchers and bug bounty hunters. We're going on a bit of a journey today, plunging deep into some seriously advanced enumeration techniques. Because look, if you're relying purely on standard crawling and passive recon, you are missing massive chunks of your target's infrastructure. So let's dive into this and start peeling back the hidden layers of modern web applications.
The overarching theme for our session today is completely moving beyond the basics of standard crawling. We're talking about brute forcing and fuzzing the unseen attack surface. We're going to get into virtual hosts, uncovering hidden parameters, and even hunting for parsing discrepancies buried deep within proxy chains. Honestly, the tools and methods we're covering today, they are exactly what separates surface-level, noisy scanning from deep, high-impact vulnerability discovery.
Here's our Recon funnel roadmap for the session. We'll hit mapping the attack surface, fuzzing for virtual hosts, bypassing automated defenses, hunting for hidden parameters, and finally, finding parsing discrepancies. Let's jump right in.
Starting things off with Section 1, Mapping the Attack Surface.
We really need to start by calling out a fundamental flaw in modern web deployments, the assumption that obscurity somehow equals security. Developers frequently and usually unconsciously rely on obscurity as a defense mechanism. They just kind of assume that if an API route isn't officially documented, or if a legacy asset isn't directly linked anywhere on the front end, well, attackers just won't find it. Because of that mindset, your standard recon techniques, like just clicking through a site or running a basic spider, they often miss the actual structural blueprints of the application entirely. To find the real vulnerabilities, we have to actively hunt for the exact things developers thought would stay hidden.
Moving right along to Section 2, Fuzzing for Virtual Hosts.
Okay, to really grasp virtual host fuzzing, you have to think about how servers actually route traffic. On one hand, you have IP-based hosting, right? A unique IP directly corresponds to a single website. Super straightforward. But out in the wild, modern infrastructure heavily leans on name-based hosting. This is where multiple host names share one single IP address. Think of the server like the front desk of a massive apartment building. It uses the HTTP host header provided by the client to route traffic to the correct internal apartment. It perfectly illustrates how name-based hosting creates these hidden rooms behind a single IP address door. If you don't know the exact name to drop into that host header, the server just isn't letting you in.
So the million-dollar question is figuring out those hidden names. And this is where active fuzzing completely changes the game. Tools like FF and GoBuster are absolutely essential for this. They rapidly iterate through custom word lists, injecting thousands of potential names directly into the HTTP host header of your request. By manipulating that header, you're effectively bypassing the surface-level routing altogether. This is exactly how top-tier researchers uncover undocumented staging environments, hidden admin portals, or even legacy dev servers that are sitting right there on the production IP, just waiting to be explicitly called by name.
Which brings us to Section 3, Bypassing automated defenses.
Now, as you scale up this kind of automated fuzzing, especially on enterprise targets, you are absolutely going to hit some friction. When you start blasting a server with a fuzzer, defensive systems like reCAPTCHA or HCAPTCHA are going to step in and block you. But what's actually triggering them? It generally breaks down into three categories. First, simple triggers, things like unusually high traffic volumes or using known data center IPs from a VPN provider. Second, passive fingerprinting. This is where the server analyzes your HTTP headers or TLS parameters to see if you actually look like a real browser. And third, active fingerprinting, where the server uses JavaScript to sniff out advanced hardware info via WebGL or installed fonts. Keep in mind, though, most sites don't actually use resource-heavy active fingerprinting. That means a huge chunk of your blocks are just caused by simple or passive mismatches in your scraping setup.
So how do we actually get around this? The entire goal is mimicking organic human behavior. First off, ditch the data center IPs and rotate quality residential IP addresses. Second, don't just relentlessly hammer the server, introduce organic timeouts and randomize your request intervals to balance your automated scaling. Third, make sure your TLS and header parameters perfectly match the user agent you're claiming to be. And finally, if you're up against active fingerprinting, you'll need to utilize headless browsers, like Puppeteer, to fully render that JavaScript. By blending in organically, your automated fuzzing can run efficiently without constantly slamming into a capture wall.
Let's push further down the recon funnel into Section 4, Hunting for Hidden Parameters.
We're moving past the infrastructure now and getting into the application logic itself. This quote from our source material really hits the nail on the head. Developers constantly leave internal-only tracking variables or critical cache bypass parameters active in production environments. They think, well, there's no input field for it on the front end, so it's safe. That is a massive, massive mistake. Undocumented debug parameters are incredibly dangerous because they usually bypass adequate validation. Finding them is literally like finding a backdoor straight into the backend. To prevent this, developers need to implement strict security controls, specifically role-based access controls, or RBACs, and ensure that undocumented legacy routes and debug parameters are completely stripped from production builds, not just hidden from the UI.
But hey, we've got to be smart about how we hunt for these, right? So, here is a quick step-by-step checklist to safely integrate automated URL parameter fuzzing into your daily workflows. Step 1. Select a highly targeted custom word list. Step 2. Whenever possible, use a staging or test environment to avoid knocking over production. Step 3. Set your rate limits. Sending too many concurrent requests can easily crash a target server, which is the last thing we want. Step 4. Monitor your HTTP status codes closely. Watch for subtle differences in response sizes, or shifts from a 404 not found to a 200 OK or 43 forbidden. This structured approach lets you balance the aggressiveness of automated scaling with the precision required for enterprise-level targets.
I really want to hover on that first step for a second, word lists. Relying purely on default generic lists just not going to cut it for uncovering the really juicy bugs. Advanced researchers build custom dictionaries. You've got to look at the specific context of your target. Are they using a framework like Spring or Django? If so, build a list that targets framework-specific parameter naming conventions. Factor in their localization and programming languages. Tailoring your word list is exactly how you discover those deeply hidden legacy API routes that the default lists completely gloss over.
Luckily, we are absolutely spoiled for choice with open-source tools to automate this stuff. For the heavy hitters, you've got Arjun, which is a fantastic Python-based tool for general parameter fuzzing across different content types. If you need blazing, ridiculous speed, X8 is written in Rust and will fly through your lists. If you prefer to stay right inside your proxy, Paraminer is an essential active plugin for Burp Suite. And GAP, or Get All Params, is brilliant not just for discovering parameters passively, but also for automatically generating custom word lists based entirely on your target's specific responses. Knowing exactly which instrument to pull from your toolkit is half the battle.
So, why does all of this matter? What's the real takeaway here? Well, hidden parameters are usually the weakest link in the security chain. Because the developers never expected users to interact with them, they frequently just skip input validation altogether. Dropping crafted payloads into these hidden variables often leads directly to critical vulnerabilities. For example, manipulating an undocumented user ID parameter might easily lead to an IDOR, or intercepting client-side parameters that get processed by the DOM can completely pave the way for DOM-based cross-site scripting, or even back-end SQL injection. And listen, when you're documenting these discoveries during a formal incident response engagement or reporting them to internal security stakeholders, emphasizing this lack of sanitization is crucial. You want to explicitly advise developers to implement strict allow listing for expected inputs and properly sanitize even those legacy routes that were supposed to be hidden.
All right, let's head down into the architectural basement. Section 5, Finding Parsing Discrepancies.
This is where we get into some really complex, fascinating stuff. A technique called differential fuzzing. Unlike your standard payload fuzzing where you're just trying to break a single application, differential fuzzing involves providing the exact same, often intentionally malformed HTTP request to multiple interconnected systems simultaneously. The goal isn't necessarily to crash them, we're looking to observe discrepancies, differences in exactly how each system interprets and parses that identical piece of data.
This is super relevant right now because, let's face it, modern web architecture is almost never just a simple client talking to a single backend server. It is a highly complex chain. A request might hit a CDN, pass through a load balancer, route through a reverse proxy, and then finally reach the backend application server. And here's the kicker. Even if every single one of those proxies is perfectly secure in isolation, chaining them together creates massive structural blind spots. If the front-end proxy parses a header even slightly differently than the backend server does, you've got a critical vulnerability on your hands.
And that brings us to Gudifu. This is a cutting-edge tool from recent academic research, and it's a total game-changer for applying differential fuzzing in production environments. Gudifu takes a guided, gray box fuzzing approach to really probe deep parsing behavior. What makes it such a massive leap over older tools is its advanced algorithm. It doesn't just fuzz a single header, it can actually search for discrepancies across the entire HTTP request. This granular, structural fuzzing lets researchers map out exactly where the proxy chain's interpretation of a request completely breaks down.
The exploitatable impact of finding these discrepancies? Absolutely massive. Minor flaws in HTTP processing let attackers pull off HTTP request smuggling, which means literally hiding a secondary malicious request inside a legitimate one, sneaking it right past the front-end proxy to execute on the back end. On top of that, these parsing mismatches regularly lead to severe cache poisoning attacks, where an attacker tricks a caching server into storing and serving malicious responses to completely innocent users. The risk profile here is immense, and honestly, the stakes change whether you're working within a private, highly controlled bug bounty program versus a wide-open public one. The deeper you go, the higher the impact.
So wrapping up this explainer, I really want to leave you with a question to chew on and maybe challenge your current methodology. Are you relying too much on standard crawling, or are you ready to actually fuzz the unseen? The techniques are all right here, from virtual host iteration to building custom word lists for those hidden parameters, all the way down to utilizing Guttyfoo for differential fuzzing of complex proxy chains. The deepest vulnerabilities demand the deepest recon. It's time to take these advanced enumeration techniques and apply them to your very next target. Thanks for hanging out with me for this deep dive, and happy hunting out there.